Hello and welcome to this Python introduction to backtracking. So what backtracking is it's not a specific algorithm, but rather it's like a strategy, much like recursion. You wouldn't call recursion an algorithm. You'd call it like a strategy or a tool you use to solve problems with the help of other algorithms. And that is similar to what backtracking is. And what backtracking essentially is starting off with is where you start off with an empty solution or a template of what the solution would look like, and then slowly filling the solution up or filling the empty solution up based on the parameters of the problem. And that is essentially backtracking. It's using recursion in a way because you have to fill it up and then constantly checking whether you have solved the problem or not, and then simultaneously using the strategy of filling it up one step at a time. And one classic competitive programming problem that uses or that you can use backtracking to use is the n-queens problem. So basically, the n-queens problem is where you start off with a board. Let's say it's a 4x4 board. And let's just fill the empty squares up with zeros because that's easy to understand. And then we represent queens as ones. And if you play chess, you know what like a queen is. I'm talking about a queen in that context, not in any other context. But basically a chess queen. And a chess queen, if you don't know, moves either horizontally, vertically, or diagonally. And the problem is, how can we place, so this is like a 4x4 board, right? So how can we place 4 queens in a way that no 2 queens attack each other? So one such solution could be like this. So this could be a queen, and then a queen here, and then a queen here, and then a queen here. So as you can see, there is a queen on each row and a queen on each column, so that they don't, none of them attack each other. And as you can see, no queen is attacking another queen diagonally either. And here is like an implementation of the n-queens problem. This is like a program that returns a single solution with backtracking. So basically, I used a class here, and then when we initialize the class, it will automatically begin solving. So we start off with this. So in the initializing function, or whatever it's called, we start off with a number, and this is basically this is going to be the size of our board. We're going to start with an 17x17 board, or you know what, let's do a 5 because that's easier to say. And then we initialize the grid or the board itself, and we use list comprehension to initialize a 2-dimensional list with a 0 in each cell rather. And then we begin solving. And if we look at the solve function, it takes a column parameter, and this is because it essentially solves the problem column by column. So let's say let's just copy this board over and then put it here. That board is for something else. I'll explain later. And we can start off with an empty board. And essentially what this code is going to do is start off or solve the problem column by column. And it's going to iterate through each column, and then it's going to iterate through each cell in that column. And it's going to start in this first cell, and it's going to try to place a queen here. And essentially it iterates through each cell here, and then it checks the validity of the position with a validity function, which is here. And we can check out this validity function first. So essentially, it takes a row and a column parameter, and it iterates through, it first checks all the cells in that current row, and it essentially iterates through every cell in that column, and checks if, in the grid, it goes through all the cells, and if any of the cells are equal to 1 or have a queen in them, it returns not valid, because obviously if there is a queen in the same row, it is an invalid position, because queens can attack each other horizontally. And then it checks the upper diagonal on the left side. So basically what that means is so if we check the validity function for the position row 2 and column 3, so this is row 0 and then 1 and then 2 and then column 3, so you can see we use a zip. We iterate through a zip generator, and it zips the following two ranges. So here we can see this range, the bottom the bottom number of this range is the row number, and here the row number is 2. So it essentially, so this is going to be the range basically, and the -1 here means it's iterating through backwards or in declining order, and it also stops at 0 because range iterates through integers and doesn't include the last one, so it stops at 0. And then the second parameter for the zip function is another range. So this time it starts with the column number, and also iterates in descending order. And what this does is basically it zips together. So if we use this example here, it zips together all the coordinates of cells in an upper left diagonal. So here we can see, here's the first part of the zip, the second part of the zip, and once these two are zipped together into a list of tuples, we can see the first cell is row 2 and column 3, which is this one, this cell. And then we go to row 1, column 2, which is this cell. And then row 0 and row 0 and column 1, which is this cell. So this is basically the upper left diagonal. And then it checks for any queens that might be in this diagonal, and if there are any queens, it returns false, not valid, since queens can attack each other diagonally. And then it checks the lower left diagonal, which is like a diagonal, but it's going left and downwards, right? And here we use the same iteration, or the same form of iteration, except this time we zip, instead of zipping like in descending order, we go through, we start off with the row number and then we iterate up. So this part is basically like iterating like this. How do I explain this? So this row is index 0, and then this row is index 1, and then index 2, and then index 3, and then index 4. So basically this one is iterating through in ascending order, and then this one is iterating through in descending order, which means it's iterating this way. So this first parameter is iterating down, and this one is iterating left. So when you're iterating down, because we're storing this board in like a 2D list with, like, this being the entire list, and then it being a list of lists, and then this will be a list, this would be a list, this would be a list, etc., etc. And if we iterate down, we want to iterate in ascending order. Okay, I really just explained that. Now moving on, it checks for queens in the upper left or the lower left diagonal, and if there are any queens, it returns false. And since return obviously breaks the function, if you're still here, it means the position is valid. And then we continue on with the solve function. And basically, if it sees that, if we try to put a queen here and it sees that the position is valid, then it tries to place the queen here. And then it checks the next row. So here it looks at, this if statement essentially checks whether or not there is a solution in the next column. So the column number plus 1. So basically, this column, it's going to check this column. Let's just index this. This is 0, and then 1, 2, 3, 4. And then this one is 0, 1, 2, 3, 4. Yeah, that's better. So it goes to column 1, and then it sees whether or not there is a solution in column 1. And if there isn't a solution, if like there's just say if there's like a if in previous columns, if we're like iterating through at column 3 right now, say, and we're trying to place a queen, and in the columns 0, 1, and 2, the queens are placed in such a way that there is no solution. If we place a queen here, there will be no solution in queen or in column 4. So like if the queens are placed like this or something, yeah, like that. Well, that ends up with a valid solution, but you get what I mean. If it sees that there are no solutions in column plus 1, it returns, and then it returns true. Well, it returns true if there is a solution in the next column. And if there isn't a solution, it does not place a queen here, and it keeps iterating. And then if we end up in the last column, if we are at the last column and we can place a queen, then we return true. And you can see here, this checks the next column by calling itself. This is a form of recursion. It keeps calling itself and keeps checking the different solutions. And if there's a dead end, it just pulls back and places a queen in a different spot until eventually there is a solution for there is a valid placement of queens for each and every column, while the entire board being valid. So we can actually see how this runs. So here, as you can see, it does return a valid solution of the n queens problem with backtracking. So it starts off in this first column, and then it goes to the second column and the third column, and yeah. So basically, let's try to see how the program would run during like when we run the program, what is happening basically. So it iterates, it comes to the first column, the first row, and it checks if we can place a queen there. Now, at this point, the rest of the board should be blank. So, you can basically place a queen anywhere, but it checks the first cell first, and it sees that, okay, you can place a queen there. And then it comes to the second column. You cannot place a queen there, you cannot place a queen there, but you can place a queen there. Now at this point, the program stops and checks. Well, it stops at this point, and then it checks the next column, and then it sees if there is a valid solution for the next column. And let's try to remember that we're at this cell, and it sees that, okay, no valid solution, not valid, not valid, not valid, valid, because nothing's attacking. But at this point, it doesn't just go ahead and record. It doesn't just go ahead and place the queens. It goes to the next column and sees if there's a solution there. Okay, not valid, valid. Now it goes to the last column and iterates through and finds a valid solution. And if at this point, for some reason, there's maybe something in the previous columns blocking, or for whatever reason there's just no valid solution, and at this point, the program runs a check of the next column after it sees that there is a valid cell in this current column, and it sort of just pauses the search once it sees there is a valid solution. And after the search comes up blank, there is no valid solution in the next column, it continues to iterate through this column. And if it happens that there is no valid solution for this column, it goes back to the last column, because we have to keep backtracking. Yeah, this is where the algorithm gets its name from. It keeps backtracking until it finds a placement for a queen in the earlier columns, with there being solutions for all subsequent columns. And okay, so this is basically what backtracking is. Okay, it starts off with an empty board. This is what I was talking about when I said an empty solution, and then it fills up the columns column by column, and whenever there is a dead end, it pulls back, it backtracks, and it changes up the placements in the previous columns until you can find a placement that allows for subsequent valid placements. Yeah, that is basically backtracking. And there are other problems beside the n queens problem that you can solve with backtracking. For example, I'm pretty sure you can solve a Sudoku with the backtracking method. I have yet to try to attempt the Sudoku problem, but yeah, I will try it later. And yeah, thank you for listening. Oh, and also a bit of background on the n queens problem. And this problem has been a problem that has been with competitive programming for quite a while. That is because up till today, there is no efficient solution to solve the n queens problem. And you might say, hey, this is you run this and it pretty quickly it returns a result. But if we go up to like higher numbers, say like 16, you can see, although it does return a valid solution, it becomes much slower than with a board of size 5. And if we go to like 17, it takes like a split second more. And if we go to 20, it just doesn't finish for a slight while, or a long while, who knows. That is because the n queens, it actually finished. Okay, cool. But with higher like numbers, it just basically never finishes, because the n queens problem really, okay, it just finished again. Okay, do not finish this time. That is because the n queens problem has an exponential time complexity. It, like, the amount of backtracking, like, eventually it just has to backtrack through like a huge decision tree, and it just, like, the CPU, or this algorithm, eventually with larger boards, it just has to go through a huge tree of possible placements, and just takes a long time. So currently there is no efficient method to solve the n queens problem, but backtracking certainly is one solution. All right. Thank you for listening, and thank you for watching, and I hope you've learned something new today. Goodbye.